Hi and welcome to video 2 of topic 3 unit 4, and this is networks and graphs, and we've been talking about minimum spanning trees in the previous video. Now we're going to put a little bit more of it into practice. So let's do that activity we did again last video and see if we can determine the minimum spanning tree for this graph. Again, I kind of think that 5 will be involved. Blue is probably not the best choice. Let's go with purple because that's the smallest one. Now that means that I've ticked off this and this vertex. If I do this 6, that's pretty nice. Tick off that vertex. I don't know whether it's going to be the minimum spanning tree. I'm really trying to avoid that 15. I don't like it. That ticks off that vertex. I've only got 2 vertices left. That looks like a 16, so I don't really want that either. But the 9 and the 8 look pretty good as well. Now, that's worked out pretty well. What if this 15 was also a 5? What would we change then? You might start getting a bit of an inkling for how we process these types of questions, because we go through here and if that was a 5, I'd probably use that 5 instead of going down to 7 and build back. You get a better understanding of how to build that minimum spanning tree. The problem comes, the thing that makes it a little bit confusing is this 10 here. We don't really need that edge. So if that 10 was actually 8 and we'd gotten to here and we're like, well, we went 9, I look at that and go, oh, let's go 8. But that would then create a cycle, so it wouldn't be a spanning tree. So it's not always that easy to do. And what we're going to do in this lesson is set up an algorithm to help make it as easy as possible. Because if you've got a large graph you're trying to create a minimum spanning tree on, then you want it to be as easy as possible. But nonetheless, that is our minimum spanning tree, and we're lucky in this case it avoided those big ones, 10, 16, 15. I'm glad you asked. This is called Prim's algorithm, and it helps us. It's an algorithm to set up determining the minimum spanning tree for any graph of any size. We just follow these rules. It's not provided for you on the formula sheet, but if you practice it, it's easy to remember. And also, it's a fairly common type question. Usually, or often, specifically asked for. Apply Prim's algorithm to blah, blah, blah. So here's the recipe format. That's why I like to call it a recipe format. Step 1, I tried to write this as simple as possible, but there is another version of this in the textbook, so feel free to have a look at that. 1, select any vertex. 2, choose the edge with the least weight. 3, now you have 2 vertices. Choose the next edge with the least weight. Ignore edges that create a loop or cycle. So this fixes our problem from the previous one. Repeat step 3 until all vertices are chosen. Done. It's kind of what we've been doing. I wrote this up as a nice big diagram as well. You may prefer this flowchart, which in itself is kind of an example of a graph or network. Have a read of that, you decide which one works for you best. I quite like recipes. So here's an example. Determine the weight of the minimum spanning tree in the graph shown. So let's start randomly in the middle here. Choose the least weight edge, 7. Now we've marked off this one. Choose the next available least weighted edge, 6. Now we've marked off this one. Choose the next available least weighted edge, 5. Now we've marked off this one. Next available least weighted edge attached to one of the existing vertices, 9. Marked off this one. 8. Marked off this one. And we've now covered all vertices. So there is our minimum spanning tree using Prim's algorithm from any vertex that will work. So it's one to get used to. Once more, determine the minimum spanning tree of the graph given. So I'm going to start on B. Okay, B, the least weight edge is 7. And then A is covered. The least weight edge available now is just 5. Now C is covered, which means I'm going to ignore the 8 because that would create a cycle. So from C I've got a 3, so I might use that 3. That gets me down to D. Now I've got some 6s floating around here, but I can see a 5 that doesn't create a cycle, so let's use that 5. I'm down to F. At F I can now see a 4, which is handy. That gets me to E. From F I can see an 8. From C I can see a 6, so let's use this 6. There it is there. And now from H and F I've only got one vertex to go, and I can get there along 2 8s. So let's say I chose this one. That would be a minimum spanning tree, but of course this would also be a minimum spanning tree if I had that and not this one. So I've got those 2 options. And it's always worth keeping that in mind. I've got those two options. But of course, is my solution unique? No, it's not. There are two solutions. So just get that in mind. You've got two possible solutions here. So there's our minimum spending tree, and that's Prim's algorithm on a fairly complex case. But as you can see, it's very procedural. Formulate, you just need to practice that procedure. Here's another example, a little bit trickier only because it's in context. Costs $200 per metre to lay a secure cable underground. Costs $300 per metre to lay a secure cable through water. Determine the minimum cost. So we're now talking about a minimum cost question, and we need to work out what these graph edges are worth in terms of costs. So, costs $200 per metre to lay a secure cable underground. That means that this is I'll do a highlight. That's a $200 per metre, that's $200 per metre, that's $200 per metre. That looks like it's $200 per metre, assuming it's this edge along here. But these are all underwater. The 90 is $200 per metre. It's $300 a metre to go underwater. So this edge, this edge, this edge, this edge, this edge, they're all underwater. So I can do a couple of things. I can sort of tinker with this in my head as I go, or I can just do the multiplication straight up. All the yellow ones are multiplied by 200. So this is $2,400 per, will be the cost to lay that. This one here is 200 times that is $4,200. 60 times 200 is $1,200. Should put the dollar sign there. 150 times 200 is $3,000. And 90 times 200 is $1,800. And then I've got these green ones. For the green ones I need to multiply by 300 because that's my cost per metre. So I get $3,000. 80 times 300 is $2,400. And 110 times 300 is $3,300. 140 times 300 is $4,200. And 70 times 300 is $2,100. And now I'm going to apply Prim's algorithm to determine the minimum cost of connecting the 5 buildings A, B, C, D, and E. So I need to find 4 edges to cover this. So using Prim's algorithm, I'll do it with a light blue highlighter. I'm going to start at A, and the cheapest first path is this 2,400 to B, and then cheapest from B is this 1,200 to there, but that takes me to this non-building. So I've got a little bit of a problem there too. So what I'm going to do is I'm going to take that back, and I'm going to recognize that I actually have to do a combination here. This 60 and this 80 have to be added together, which gives me a total of 3,600 for that total cost up there. So they're gone. And the 210 metres, because of the way it's written and the way A to C is connected, I'm assuming that carries the whole way. So there's some information, maybe assumptions based on this question because it's a little bit ambiguous, but I'm going to call this whole thing, so this whole distance from B to D is 140 metres and $3,600, part on ground, part underwater. So let's go back to the question. I've done the first leg. Now it turns out that $3,600 is not actually as cheap as the 3,000 option here. And I've got a 3,000 option here, which means potentially I could end up with multiple solutions. But I've got 4,200, 3,600, I've got 2,100 available, so I'll take that. And I've got this 3,000 here is my last available edge, and they're all my cheapest ones. And so, oh actually no, my apologies, I won't take that 3,000. I will still take that 2,100 and I'll take this 1,800. And you can see what's happened here is I've pretty much avoided the water most of the time, except for that one crossover, the cheapest water crossing, and that kind of makes sense because the water is more expensive. So there is, through an application of Prim's algorithm, the cheapest possible way to lay these cables in what is a slightly ambiguous question, so it would allow you to discuss the reasonableness of your answer. And I've already mentioned a couple of things. So underwater is more expensive, we only cross over once. We kind of expect that. Not necessarily going to be true, but we kind of expect it moving forward. And of course we had that little bit of ambiguity, so we talk about that in the reasonableness as well. So the question for you, success criteria: can you sketch and use a weighted graph? Can you identify a tree and spanning tree? Can you determine a minimal spanning tree using Prim's algorithm or otherwise? And you can also work out hopefully the weight of the minimum spanning tree. So this question said determine the minimal cost, and so I should probably do that now that I've even talked about success criteria. The minimum cost will be equal to 2,400 plus 3,000 plus 2,100 plus 1,800, and of course if we add those we get 5,000, 7,000, 8,000, 9,300. So that is our total weight of this minimum spanning tree, the total cost. A very simplified example. There's obviously other things associated with the context, but that's what we're looking at mathematically. There is a final example here, but I will do that on a separate video. All the best.